Hello. So you can notice that we are horizontal today. So a few comments about the Fresnel Integral via the Feynman trick. I released a short about it, and in there isn't quite enough time to explain everything very well. I have to skip a lot, though things are relatively straightforward. I don't think they're obvious at all. Uh, at least not mostly. Let me take something here to point instead of my fingers. Tired of my fingers. So the Fresnel integral is the integral from 0 to infinity of sin of t squared dt. We've done this already in the channel, in the short, in the complex plane, and there are other ways, in fact, of doing this. But for our purposes, we are gonna solve this via the Feynman trick, which is gonna be basically this step, and that will actually help a lot of things go on. So the first thing we do is substituting t squared by x, and t is gonna be the square root of x. This is also one of the most important steps because of this square root that's going to appear because of this. And the 2t dt is going to be dx. So we need to make t's appear above and below a fraction and 2's appear above and below a fraction, which is exactly what we do here. So we have 2t dt to become dx. We have d squared that's equal x, that's gonna give us the sin of x. And we have this 2t left over. 2 times t is 2 times the square root of x. So that's a good start. Is this integral a lot better? Not really. But we can make a little magic happen, as in we're gonna multiply by square root of pi above and below, so that we have the square root of pi divided by 2 times x. And this is the integral of the Gaussian from 0 to infinity with the parameter x. It's fairly easy to obtain the Gaussian even via the Feynman trick, actually. Another Feynman trick, not this one. But if you know this, and I know this, you can plug this here, integrate in x and then in t, so that we gain, integrating in x, a sin times exponential integral. Sine is basically a glorious exponential that oscillates, as in it's a complex exponential. Well, it's actually a linear combination of two of them. So it's easy to integrate this product. So this is the motivation to do this. Because what will happen is that we will have only 1 divided by the exponential thing multiplying x as the leftover things, and we will have only the variable t. So we indeed here are gonna go from 1 dimension to 2 dimensions, and most Feynman tricks actually do exactly that, but in an easier way than the usual Jacobian paths usually have to do. The thing about Jacobians is that they transform the way you subdivide the space. And in here we kind of avoid this because we work on each variable only once and only linearly. or independently at most, so that even if we change the way the space is subdivided, uh, we are changing each variable individually. So we don't have to calculate the Jacobian. It's just a stretch and compression type of deal. And that's a lot easier to deal with. Oh, I forgot to tell about the fact that from 0 to infinity, it stays from 0 to infinity when we go from x to t squared. This is the type of detail that you can't forget the next few times, because we are gonna do a lot of those. So this is just a remember where we started. So we are now here with the integral from 0 to infinity of dx sin of x by the square root of pi times the integral from 0 to infinity in dt tilde, which I just call tilde in this short because the tilde, in fact, comes with a second that I didn't have there, times the exponential of minus xt squared. So this is a Gaussian in t, and x is a parameter for this thing. So let me just give it a little bit of a rest for one hand for a second. So we have this Gaussian here times the sine. We're gonna get them together, use the Fubini's theorem so that we can invert the integrals. We're gonna integrate in x. We're gonna express sine in terms of exponential, so that we have this. This 2i comes from the sine. And this is a sum of exponentials, so the integral is the exponential divided by any coefficients times the x. And that's going to be the integral in dx, so that we obtain this thing here, this slight monster. I won't comment on all the signs that are going on here, but rest assured that I made at least 3 mistakes in this part. But after you do all mistakes, you finally arrive to the right signs. Regardless of that, of the many sign possible errors that you might have here, you will know that the integral in the infinities is going to vanish, and the integral at zeros will make this go to 1, so that after you massage this somewhat thoroughly, you're going to obtain... This is not a lot of massage here, in this step at least. There's a little bit of massage between here and here, because you have to place both things in under one fraction. You are gonna have two numerators that are different and that are gonna sum to 2i in the end, so that they cancel this 2i. And that will eventually give us 1 divided by the square root of pi. This is literally boring, a very boring step actually. And this will give us 1 by the square root of pi from the times the integral from 0 to infinity of dt tilde divided by t tilde to the 4th power plus 1. T tilde was a very unfortunate choice for variable name, because it takes a long ass time to say. We're gonna make a 2 appear here, so now we have a thing that we're gonna do that is a bifurcation in our paths here. So you don't need to do this exact trick that I'm gonna do right now. You can separate this via a factorization and via partial fraction. I am going to do that method too. Both of them are gonna work. I think the partial fraction is a lot longer. In fact, I think even the complex plane is shorter actually, because you have to do the partial fraction math, And in this case, there will be a square root, and the square root of 2 is gonna bother you quite a lot in here. So we have this, and now we make a 2 appear because we want to make this have a square type of structure so that we can separate in 2 terms. Basically, this is the idea. So we're gonna make a 2 appear, and we're gonna sum and subtract t squared, and 2 is gonna be 1 minus minus 1, so that we have 2 terms, and the 2 terms will integrate entirely differently. So what will happen is the following. This 2 below is this 2. This term is going to be this term is going to be this term, this minus is going to be this minus, and now we're going to divide everything by t squared in this term between parentheses and in this term between parentheses. This is a thing I made a mistake the first time I released the short, and then I was thinking about the integral that I had written instead of this, and I was thinking, I don't think this converges, and it didn't converge. And in fact, it didn't cancel either. We have to have this t2 minus 2, in fact, to do this trick. It is fundamental. That integral was somewhat interesting too, to be honest, but it was a mistake. So now we have 1 plus t2 minus t2 to the 2 minus 2 to the power minus 2 dt2 divided by t2 to the square plus t2 to the 2 minus 2. So remember, we divided everything by t squared above and below, which we can't because it's doing the same thing above and below the fraction, so it's entirely copacetic. What's the advantage we got? Well, if we may complete this square here, we're gonna call this another variable, and this variable call is gonna give us oh, it's even wrong here because I forgot a sign. Oh, it's wrong in the chart too, by the way. I'll have to make a comment later in the chart, unfortunately. So we will complete both squares similarly to each other, but with the signs different, so that this thing is going to be the thing that our variable substitution will spit out. And basically we do the same with the other term, so that we finally arrive at the 2 variable substitutions that are crucial to solve the problem. So we're going to complete this square. To complete this square, we're going to use minus 2 plus 2, so the minus 2 goes inside, the plus 2 remains, and in here we're going to do the inverse. We're going to do plus 2 minus 2. The plus 2 going to go inside, and the minus 2 is going to remain. Why this order? Because this sign drop is going to happen, so that this becomes the thing that is derived will become positive, so to become this, and the converse happens here, so that u is going to be t tilde minus t tilde to minus 1, that's going to be equal u, so this is u squared plus 2, and this is the derivative of our change of variable, times the t tilde, which is this term, and that's equal to du. Incidentally, this change of variable here is going to give us a variable that's go from 0 to infinity, that will go from 2, an integral from minus infinity to infinity. How that works? Well, we're going to approach the infinity from the positive side, because everything here is positive. And going to the positive side, which is more rigorous than what this suggests actually, we're going to have that at 0, this is 0, and at 0, this will go to minus infinity because of this minus here, because this positive term goes to infinity if we approach the infinity from the right-hand side. And in infinity, this gives us infinity, this gives us 0, so this is go from minus infinity to infinity. So this is u. This integral becomes this. So this 2 remains, this is u squared, and this entire thing is du. What about the next integral? Very well. 0 will become infinity. Why? Well, this is 0, but this from the right-hand side gives us infinity, and infinity gives us infinity too, so this integral doesn't contribute. And you might ask yourself, isn't this weird? In fact, if you knew what was the primitive from this step, which is possible, I must say, it is yet another method of doing this, by the way. You will know that one of the integrals is gonna have the character of a logarithm of a this is gonna be a quotient, an absolute value of a quotient of two polynomials, one divided by each other, which is gonna result in nothing in the end for us and for our purposes. And in this integral, the change of variable takes care of that for us. And now we have basically already an arctangent integral. It doesn't matter which method you prefer here. You can divide this by 2, so you put inside the square root of 2 here. So you put inside the square root of 2 here. Since you had to make 1 appear above, you have to make 1 appear below. You change variables, you go to z. I didn't put even the z change of variable because it's kind of obvious from this. So when this is minus infinity, it stays minus infinity. When this is plus infinity, it stays plus infinity, because this is a linear transformation from here to there. I already put this factor here. The factor of the linear transformation already appeared. And we are basically at the arctangent, so we just integrate arctangent. There are ways of knowing this is the antiderivative of this function is arctangent. You can go from here to there, actually. All of those things don't matter for us. We just want to do the integral. So we're gonna carry all those factors, half of 1 divided by the square root of pi times 1 by the square root of 2, arctangent from minus infinity to infinity, and that is equal to pi divided by 2 plus pi divided by 2, because there will be another minus here, because it's going to be pi divided by 2 minus pi divided by 2. So we get pi as the result here, and 2 inside is going to give us a square root of 8, but this is the square root of pi squared, so this gives us the square root of pi divided by 8, which was the result we expected from the integral using the complex plane. And yes, I went a little bit over explaining. This could have been done in like 15 minutes, but as I promised, in this step here, there was a way of doing this with partial fractions. So how does that work? Wait a sec. So this was the integral that we had. this can be factored in this way: t squared minus the square root of t plus 1 times t squared plus the square root of 2t tilde. Is this oh, it's right, plus 1, so the minus here and the plus here. It's somewhat evident, you just need to expand to know this happens. This gives us an idea of separating both parts by partial fractions, which is gonna be this long thing. Nothing fancy happens here. So we establish this equality, we make a common factor between things, and we get the cube potencies equal to each other. So there's no cube potencies powers equal to each other. So there are no cube powers here. There's only order 0 powers here. So all cube powers are gonna equal to each other. So a plus c equals 0. The square powers, there are quite a few terms that are gonna be squares. If I am not mistaken, those are the square powers. The linear powers are gonna be this one. If I remember correctly, it's either this or that. It doesn't really matter, because what matters are the equations that you arrive at, and these zeros especially. So just gonna open this up and analyze who has t tilde cubed, t tilde squared, t tilde to the power of 1, and t tilde to the power of 0. Remember that to the power of 0 we have one guy here, one that we have to consider, only one term will have that. And you solve this as you solve 4 variables for 4 equations normally. So I did this here. BD is going to be 1, A plus C is equals 0. So this means that A is minus C. So we can put, instead of C minus C, A everywhere. After we put that everywhere and we recognize that A plus C is 0 from this, we obtain the relation between B and D, which is equal and they are both half. If they are equal and are both half, this means that B plus D, no, this means that A plus C to be 0 will, from plugging in this expression, gonna give us that A is equal minus 1 divided by 2 the square root of 2, which means that C is gonna be 1 divided by 2 the square root of 2 positive, which will give us this horrible thing here. It's not as horrible as it seems. So it's 1 divided by the square root of pi times 1 divided by 2 square root of 2, the integral from 0 to infinity of minus dt tilde times t tilde minus the square root of 2, t tilde minus 1 divided by the square root of 2 square plus a half. Here I already did a trick of completing the square that I'm gonna repeat in the other term, and those two terms are the terms a, b, c, d, of the partial fraction separation. So, in here already completed the squares, and now I'm gonna multiply by 2 because I want this to be 1. So if I multiply by 2 below, I have to multiply by 2 above. So naturally this happens. I'll put the 2 inside the square. So this square root becomes a minus 1, and this lack of square root is gonna be a square root. 2 and above is gonna only result in more 2's, so 2t tilde and 2 square root of 2. I'm putting this just so I can do this. And the same thing happens for the other term, kind of symmetrically. And the symmetry here is gonna actually progress, because after doing some calculations of what will happen if we do a substitution that seems interesting, we're gonna come to the conclusion that we're gonna need another square root because of this square root here. So we need to make a square root of 2 appear above and below. So to appear it above, we're gonna absorb in the above terms, and in the below term, it's gonna combine with this square root of 2 to make it become a 4, so that we will rewrite this in a more interesting way. That is this big term. I am not saying all of this. I'm sorry if you're blind in learning calculus. If it gives you any solace, it's just 4 terms in which 2 of them are gonna give you an arctangent integral, and 2 of them are gonna give I was pointing to the wrong two terms actually. 2 of them are gonna give you an arctangent integral, and 2 of them are gonna give you a logarithm integral. So that should be enough for you to proceed if you're blind and are somehow watching this video. And I need to make 4 variable substitutions here, so bear with me for a second. So in the first term here, we have another square root of above and below, because I forgot doing how do I say this, chain rule. I forgot a chain rule. I later realized. And this is what these 2 square root of 2's above and below are. And so it's the square root of 2 times dt tilde times 2 square root of 2 t tilde minus 2 divided by the square of the square root of 2 times t tilde minus 1, and after closing the parentheses plus 1. This term has a leftover term that is plus the integral from 0 to infinity of the square root of 2 dt tilde times the square root of 2 time divided by the square root of t tilde minus 1 square plus 1. And the other terms are similar, but instead of minuses, we have pluses, including this minus outside here. So what are the changes of variables? Well, 2 changes of variables say that the square root of t tilde square plus minus 1 squared, no, let me start again. The square root of times t tilde plus or minus 1 squared is going to be either p or r. I chose p to be minus and r to be plus. And in the leftover terms, the square root of 2 times t tilde minus 1, so no square, is going to be q, and if it's plus 1 instead of minus 1, it's going to be s. So the q and the s substitutions are going to give us 2 terms of the form that are going to give us an integral that's an arctangent. Don't forget that at 0 this is minus 1, and that at 0 this is 1. This is important because another cancellation is going to happen because of this. And in here, do not forget also that at 0 r is going to be 1, and at 0 p is going to be 1 as well. And those 2 terms are exactly the terms above for the p and the r substitution terms. So what happens is that they will have opposite signs and will cancel each other, just like they did cancel in the other method. So we don't even have to evaluate them, which is good because stuff would would explode, actually. So luckily it's one integral minus the other. And we have a square root, this square root here, that is left over in both terms. So we put that aside. We still carry the 1 divided by the 4 times the square root of pi outside. And then we have to take these two arctangents and calculate them from -1 to infinity and from 1 to infinity. So arctangent is equal to -1 when the angle, the arch whose angle is going to give us a tangent that is -1 is minus pi divided by 4. And the arc whose tangent is going to be 1 is going to be an angle that is pi divided by 4. And for infinity, it's going to be pi divided by 2 in both cases. So we have pi divided by 2 minus pi divided by 4, so plus pi divided by 4. So we have pi divided by 2 minus pi divided by 4. So that we are finally arriving at the answer, which is 2 pi divided by 2 of this, divided by 2 square root of 2 square root of pi, which is going to give us the result that we already arrived at, square root of pi divided by 8. Yes, this was very complicated. That's it. Bye for now. Yes, it was a lot longer than you would think, huh?